Hi everyone, my name is Wuxuan Shi, a PhD candidate from Wuhan University. I'm glad to present our work, Symmetric Uncertainty-Aware Feature Transmission for Depth Super Resolution. When humans understand a scene, they can not only get its appearance, such as color and texture, but also capture depth information to produce stereoscope perception. The perception of scene depth can promote research in many fields, such as 3D reconstruction, autonomous navigation, pose estimation, and so on. These tasks usually require high-quality depth information. In application scenarios, consumer-grade depth cameras are typically coupled with RGB sensors. However, the resolution of depth maps is difficult to match with RGB images due to the limitation of depth sensor imaging capability. As a powerful solution for this issue, depth super-resolution has attracted increasing attention. We can use DSR to obtain HR output from degraded depth maps while recovering lost high-frequency information. RGB images usually have much larger resolution than depth maps and have strong structural similarity with the registered depth maps. Therefore, as shown in the figure, we can use the registered HRGB image to guide the reconstruction of the LR depth map, and this method is called color-guided depth super-resolution. Although existing algorithms have achieved impressive performance, there are still some unsatisfactory aspects because of two challenges. Firstly, the resolution gap between the paired HR-RGB image and AR depth map leads to the difficulty of directly fusing RGB features with depth features without any upsampling operation on the original depth map. Because of this challenge, it is impractical to directly apply the post-upsampling structure, which is commonly used in single-image super-resolution methods. Previous work would typically start by using interpolation to upscale the depth map to the same resolution as the registered RGB image, called pre-upsampling. However, this strategy frequently introduces side effects such as noise amplification and blur phenomenon. Therefore, how to make the depth features and RGB features consistent in spatial size while avoiding the above side effects is an important issue. The second challenge is called cross-modality gap, where the edge and texture of the depth map do not always match the registered RGB image. As shown in the figure, there is a strong similarity in the texture of red box region in both the RGB image and the depth map. In contrast, the complex texture in the green box region of the RGB image presents inconsistency with the smooth texture in the same position of the depth map. Existing methods usually have two branches or subnetworks, one for extracting features of LR depth maps, and the other for extracting features of corresponding HI RGB images. To provide guidance to DSR, they concatenate the RGB features or the extracted RGB high-frequency features with the depth features. However, due to the cross-modality gap, not all high-frequency information of the RGB images is required for depth map reconstruction. Such approaches tend to transmit mismatched texture information, causing texture copying artifacts and depth bleeding. So, for color-guided DSR methods, it's crucial to accurately estimate the regions of the RGB features that do not match the depth texture during feature transmission. For the resolution gap, we build an iterative up and down sampling pipeline to replace the commonly used interpolated pre-upsampling in existing methods. Especially, we upsample the depth features before each feature fusion to make them spatially consistent with the RGB features and projected the HR features back into AR spatial domain after each fusion for subsequent operations. This structure has been proved to better mine the deep relationship between AR and the HR image pairs. Meanwhile, we can eliminate the resolution gap while providing an error feedback mechanism for projection errors at each fusion stage to elevate the noise amplification and blur. For the cross-modality gap, we design a novel symmetric uncertainty scheme via a simple yet effective flipping operation for the uncertainty estimation in feature maps. Here we provide a visual experiment to present our idea of estimating uncertainty. Depth super-resolution is an ear-post problem, as one input AR depth map can be originated from a variety of HR depth maps. For any pixel in the predicted depth map, all possible outcomes for each pixel constitute a distribution U, where I and J denote the spatial coordinate of the pixel. Mu and the square of sigma represent the mean and variance of the distribution respectively. The uncertainty of each pixel is bound up with its variance. Given an LR depth map and an arbitrary DSR network, we feed both the LR depth map and the horizontally flipped LR depth map into the network to obtain two horizontally mirrored HR depth maps. After flipping again, the two depth maps are spatially aligned. The super-resolved depth maps are equivalent to sampling all possible corresponding HR results twice. The difference is generated between the two samples by convolution, and the spatial transformation increases the difference enough to characterize uncertainty. We estimate the spatial distribution of the standard deviation by computing the pixel-wise absolute difference between the two samples. It can be seen that the uncertainty in the texture and edge regions is much larger than in the smooth regions, which allow the network to know where in the depth map is difficult to depth super-resolution. Regarding how to use symmetric uncertainty, we multiply it with the RGB features. RGB features corresponding to regions with greater uncertainty in the depth map are given higher weights. Another advantage of our scheme is that the calculation of symmetric uncertainty requires only one forward propagation. Combining the above two ideas, we propose symmetric uncertainty-aware feature transmission (SUFT). The up projection and down projection units are achieved by convolutional layers, which provides difference for later uncertainty. The overview of our network is shown in the figure. We embed our SUFT module into a multi-stage fusion network, which consists of two branches. To evaluate our method, we conduct sufficient experiments on NYU-V2, Middlebury, and RGBDD datasets. We train our SUFT network on NYU-V2 dataset and test it on the above three datasets to verify the performance and generalization ability of our method. Here is quantitative DSR results in average RMSE on NYU-V2 dataset and the Middlebury dataset. It shows that our method outperforms the SOTA methods on all scaling factors. On RGBDD dataset, our method also achieves the best results even in the more challenging real-world manner. Here is the visual result under the scaling factor of 8. In terms of the overall and the details of the results, our proposed SUFT can reconstruct the depth information more accurately without introducing texture cropping artifacts and extra noise. We also compare the DSR results on NYU-V2 dataset and RGBDD dataset under different experimental settings. As shown in the table, both iterative up and down sampling and symmetric uncertainty bring substantial improvements. To further analyze the effective of symmetric uncertainty, we conducted the visualization experiments. The first column is the symmetric uncertainty map, which highlights the hard-to-recover areas in the depth map. The cross-modality gap can be clearly seen by comparing the depth feature map and the original RGB feature map. We use a high-pass filter to obtain the high-frequency components of the depth feature map. It is noticeable that original RGB features contain some high-frequency information that does not belong to the depth modality. Besides, we also visualize the RGB features processed by symmetric uncertainty, which is very close to the high-frequency components of the depth feature map. Compared with simply transmitting unprocessed RGB features to the depth branch, our proposed symmetric uncertainty can provide a more effective guidance and avoid triggering texture copying artifacts. To conclude, in this paper, we propose a novel symmetric uncertainty-aware feature transmission (SUFT) for color-guided depth super resolution. For the resolution gap, we build an iterative up and down sampling pipeline in feature transmission instead of interpolated pre-up sampling to supervise noise amplification and blur phenomenon. For the cross-modality gap, we propose symmetric uncertainty, which attempts to precisely select the effective information in RGB images, avoiding inconsistent textures. Finally, our method achieves superior performance with clear margins on benchmark datasets and challenging real-world manner settings. We also provide ablation experiments to analyze the influence of each component in the model. Thank you for your listening.